Hello everyone! During this session we're going to explore Falco and its unique approach to tracing things from the kernel up to provide the last line of defense in cloud-native security contexts. In an in-person conference I would have asked the audience, hands up who already knows what Falco is, but I'm not sure how this is going to work in a virtual conference, so let's move on. Before to start, briefly a bit of history. Falco was created as an open source project from day one by sysdig in 2016 to parse libsysp events. Libsysp is another open source project from sysdig to match security threats against syscalls. About 2 years later, it was donated to the Cloud Native Computing Foundation, a branch of the Linux Foundation, becoming the first CNCF sandbox runtime security project. It gained some traction, to the point that me and the other maintainers had to start a weekly community call, to which, by the way, I invite anyone to participate every Wednesday at 5 p.m. Italian time. And this January, finally, Falco has been the first ever runtime security project to be promoted to the CNCF incubation level. Anyways, my name is Leonardo. I'm an open source software engineer at sysdig, where my daily job is to code Falco, evolve it, and maintain it. In case you're wondering, yes, I'm one of its maintainers, so I spend all day on GitHub. You can usually find me on Twitter, GitHub, and generally the web with the nickname Leodido. Feel free to drop me a line, follow me, send direct messages, ask questions, no problem at all. So the plans for the next 20 minutes are to first describe the context and the environments Falco is made for. Then we'll talk about how it approaches and solves the detection problem for security anomalies. And finally, we'll have some fun together watching how it's able to detect potentially malicious behaviors. So what does security mean to me? How to characterize the security problem? I don't know you, but I personally don't want anything happening in my systems without me even noticing it. I want to control things that can happen and things that cannot. Since preemptive control is not always possible, I also want deep visibility into my systems to be able to know as soon as possible what just happened. Basically, I think of security in terms of two words: prevention and detection. What the two words have in common? Policies. Both concepts use some kind of policies to describe the allowed or disallowed behavior for a process in terms of system calls, their arguments, and thus resources assessed. The differences are that the first word, prevention, is connected to the concept of enforcement. Do not allow some actions for some persons to happen at all because of the policies. Tools in this category change the behavior of a process by preventing system calls from succeeding, or in some cases also killing the process trying to perform those actions. On the other side, the second approach to security is to use the policy to monitor the behavior of a process and notify when it steps outside the policy. Thus, we can also think of these two aspects of security in terms of enforcement and, not versus and, auditing. Some examples of enforcement tools are seccomp, eBPF, Linux, AppArmor. I bet everyone here knows. Even the authorization mechanism, like the admission controllers and the role-based access control for Kubernetes, fits this category. While tools like AuditD and Falco itself belongs to the auditing side of the security topic, a topic that, especially in cloud-native environments, has not been solved yet. Can Falco solve all our concerns? No. Security is made of layers, and Falco is here to be one of them. You will have to combine it with other layers in many ways. The first example that comes to my mind is to use Falco to identify malicious attempts to access sensitive resources by observing the whole behavior of your environments and then write enforcement policies that will prevent the episode to happen again in the future. Basically implementing a sort of feedback loop, continuously improving the security posture of our environments. Since Falco runs mostly userspace, this makes it somewhat a softer target. But on the other side, this also makes it able to have a much richer set of information powering its policies. Unwanted kind of policies that's very difficult to implement completely at the kernel level. On the other side, Are enforcement prevention tools enough? Before to answer, let me ask you some more questions. How to trust cloud providers and their ability to detect malicious or compromised insiders? How to prevent an undisclosed vulnerability or 0 days that allows someone to break into your systems? I mean, CVE still happens. Linux, Kubernetes, whatever project. Name a project that has not experienced a CVE and suffered an exploit. It does not exist. What I want to say is that prevention alone is not enough, and these two approaches to security are and must be, in my opinion, complementary, not mutually exclusive. So since it's clear that there's no such thing as perfectly safe and perfectly secure software, runtime security is basically the last line of defense. Think of it this way. I have put locks on my doors, compliance rules, but if I don't use them, policy violation, or if someone breaks my window, anomalies, 0 days, I'm also glad I have an intruder alarm, Falco, to alert me telling exactly what happened in detail. Prevention is about locking the doors, detection is about monitoring the inside. And the Falco unique way to do this is by tracing and detecting everything happening inside your box, from the bottom, the kernel, up, instead of using the usual top-down approach. How that's possible? Tracing syscalls where they happen, in the kernel, and asserting rules against events containing the syscalls plus other context info like arguments, Kubernetes metadata, container metadata, and so on. But somebody could argue at this point, but why tracing the syscall? Let's look at what we have today. Here on the side I tried to draw a diagram to represent the nowadays usual setups. Our production environments are filled with so many pods, services, containers, tools. It's very complicated. And well, it turns out that this complexity is the exact reason we should go look under the hoods, if you think about it. In the end, whatever program you run, it will end up making a lot of syscalls, disregarding the syscall wrapper it uses. This is because system calls are the way programs ask the kernel, where everything really happens, to perform some task. Whether the task regards networking, I/O, processes, and so on, this does not matter in reality. Thus, instead of looking into every one of the hundreds of layers and abstraction we run our applications onto, which is even more valid argument with the whole cloud native storytelling, the Falco approach to detect security threats is to go at the lowest possible level and trace all the footprints and the context in which they happened. Finally, combining these signals with metadata from other layers of interest like Kubernetes audit logs, container metadata, and so on. But to do this, a set of unique challenges arises. Syscalls are basically the API that abstracts all the hardware for us. They are a very powerful mechanism, but not very much from a user space perspective. To bring every syscall happening to user space, for example, you have to do another syscall. And guess what you have to do to know the time an event is happening in the kernel? I mean, time is important in the security context. Well, guess what? Another syscall. Except for the very braves playing with RDTSC and things like that, but that's another story. So, also, syscalls are a lot. And with every new kernel release, they can change, gain a new parameter, new syscalls can be introduced, old ones deprecated, things change, so it can be really, really painful. To complete the complexity of the picture, try to imagine a system able to keep up and process millions of syscalls per second in real time, plus their context and their arguments, because this is what happens on our machines, millions of syscalls per second. Also, we want to combine this huge flow of kernel events with data from other various tools that are very common in today's very complex setups, because we know that syscalls alone will not be enough to create a software that deals with runtime security. For example, we want to connect these events we're detecting with Kubernetes metadata or also with data from container runtime. But the Docker daemon, container the API, that kind of things are way slower than syscalls, right? So Falco does the whole thing asynchronously and reconciles them later. This is all Falco does in words. We are gonna deep diving into it right now. But before, let me ask you of myself, last question. How to get syscall to userspace? What approaches do we have? What solutions can we implement? The first option is to write a kernel module for that, right? Which comes with a lot of downsides, both on the development side, kernel panics, and the deployment one. Imagine telling then your customer, hey, a new version of Falco has been released with a new Falco kernel module too. Please reinsert all the modules to all your 300 machine fleet. I mean, it's painful. An alternative that we have is to implement an eBPF probe that has feature parity with the kernel module. I think that today almost anyone heard about BPF, right? Unfortunately, I cannot spend 20 minutes talking about BPF in this talk. I would love, but I cannot. But in case you want to know more about BPF, I suggest you the book from my friend Lorenzo, or go to listen to my podcast for Google about BPF. I put the links at the end of the deck. Basically, the advantage of BPF is that you are able to code the kernel to obtain the syscall in a safer way, since its code is run into a dedicated virtual machine with an emphasis on security. Except when this virtual machine has security bugs, but also this is another story. So we have this concept of Falco drivers to produce syscall input events for Falco. In reality, we have 3 drivers: the kernel module, an eBPF probe, and recently we introduced a ptrace-based producer called pdig, which you can find on GitHub Falco Security Organization. It is slower and very hacky, but helpful in some environments, like managed Kubernetes clusters, Fargate, places where you cannot install a kernel module or eBPF probes. In such case, you cannot use the high performance in kernel tracing mechanisms, but with pdig you can still run Falco and let it trace all the syscall thanks to magic with the assembly trampolines. Clearly, there are also other ways to implement this, but I invite anyone that has other ideas to come to the weekly community calls of Falco and propose them. We would love. There's a diagram describing how Falco works when using the Falco kernel module as an input driver. As you can see, there's a separation between the kernel space and the user space, at which boundary sits Falco. The kernel module attached to the start of execution of every syscalls and also to the end of syscalls executions. It grabs the arguments, it augments this info with contextual information coming from the operative system with a mechanism we call fillers, and it finally puts all this inside the ring buffer. Well, it actually stores the pointer to the memory containing this data in the ring buffer, thus effectively sharing data. But wait a minute, what's this ring here at the middle of the slide? It's a ring buffer, an elegant circular data structure with a fixed size, 8 MB in our case, that acts as a first in first out queue. It's a very important piece of Falco architecture because having millions of syscalls to trace puts a hard requirement on performances in order for Falco to be effective. So the ring buffer is the ideal choice. It does not require elements to be shuffled around when one is consumed, and it gives us access to data in constant time. The ring buffer is then consumed in user space through the devices by libscap. In fact, when using Falco with the kernel module, you will probably notice a bunch of devices, one per CPU, del Falco 0, del Falco 1, and so on. Those files are the concrete implementation of the communication mechanism between kernel and user space that I just described. After this step, libsysp enriches all this data coming from the kernel, executing callbacks to grab things like container metadata, do you remember? Finally, the Falco engine asserts the current rule set, the one loaded by the user, against those data and eventually throws alerts, outputs. Then you have companies that want to use Falco, but they cannot install the kernel module. and they ask you how to do, and we reply them, well, we got you, no worries, we have developed the same functionality with this new kick-ass technology called the eBPF. In this case, as the diagram shows, there's no ring buffer involved, because eBPF does not allow you by design to move memory from the kernel space to the user space, and for reasons, I mean, the eBPF purpose to be safe would have been completely false soap in that case. But luckily, eBPF has a mechanism called eBPF maps. So in this scenario, libscap, the library that before was reading the devices, loads the health of an eBPF program into the kernel eBPF virtual machine, where the eBPF verifier makes sure you don't mess up with the kernel and executes it. In reality, libscap also send little eBPF programs to be executed at runtime to augment the traced syscalls, the famous fields we mentioned before. So that in an event, you see the actual value of a syscall parameter head, not some random hexadecimal values. This is what fillers do. At this point, the data flows back to libscap and libsysp thanks to those fancy BPF maps, and libsysp can again do its magic enrichment. All this said, what remains on Falco to say about Falco is that it is just a continuous loop that reads those input events and then outputs alerts about security threats you declared with Falco rules when the engine finds a match. We will see now that the language has also advanced operators and filters provided by libsysp to make things easier. This is an example of a rule that we are going to see it in action now. The language, as you can see, is very simple. It's a YAML subset, and this makes it very easy to learn and to adopt, unlike the policy languages of other tools in the security field. Well, since it's YAML, it's very hard to indent correctly, but that's not Falco rule's fault. Let's see this rule in action. Okay, so here we have the rule that was in the slide. We created a drift YAML rule set because we don't want to use the whole Falco rule set that contains a lot of rules. As you can see, this rule is using isopenexec, which is one of the utilities that libsysp provides us. We check for the type of syscall happening, we check that this is happening into a container and other cool things. The idea is that when someone runs a container and tries to create an executable file, Falco should alert us. So let's run Falco with this rule set. Okay, Falco starts. Let's now run a container. V. Okay. Okay, let's create a file with C with execution permission. The file is named blah blah. Let's now compile it and execute it. And as you can see, error drift detected, open plus create, new executable created in a container. The Falco output also says tells us the command that has been executed and the name of the file. So, yay! Let's now come back to the slide because we have no more time left. Bad things happen, right? For example, recently a CVE on Kubernetes has been found and it affects a lot of Kubernetes versions. I have no more time to talk about this, but I put the slides here so that you can deep dive into them and detect before to upgrade a Kubernetes how to mitigate this CVE or at least alert your SREs about this. There are rules to do it here. This is the slide with the resources to know more about the BPF, ring buffer, fillers, Falco the full rule set, I hope that everyone enjoyed this presentation. Thank you everyone. Ciao.